Welcome to the session on vectors, review exercises. The objectives for this session are to review previous topics through exercises, namely, use column vectors and carry out arithmetic operations on vectors, calculate the magnitude and direction of a vector, use vectors to solve geometric problems, and find the position vector of a point dividing a line segment in a given ratio. We will now solve the review exercises shown on your screen. Pause the video and have a go. When you are ready to view the solutions, press play. Before solving the first exercise, we're going to take a look at some theory which will help us to solve it. A vector can be described using its displacement or change relative to the x and y axes. This is called a column vector. For example, the diagram shows the vector a equals 3, 4. How do we multiply a vector by a scalar? When multiplying a vector by a scalar, each component must be multiplied by the scalar. So lambda times pq equals lambda p lambda q. When we add two vectors, we add the x and y components. So x1 y1 plus x2 y2 becomes x1 plus x2 y1 plus y2. So here's the first exercise. So let's solve part A first. We are required to find 3a. So 3a equals 3 times 3, 8. We multiply the x and the y components by 3. So 3 times 3 and 3 times 8 to give 9, 24. And now for part B. Let's solve this. A plus b equals 3, 8 plus minus 1, 4. Add the x components and the y components to give 2, 12. And finally for part C, let's solve this. 3a minus 4b looks like this. Multiply a by 3 as shown and multiply b by minus 4, or multiply b by 4 and take it away from 3a as shown. To give 924 minus 416. To give 13, 8. A vector has both magnitude and direction. You can use Pythagoras' theorem to calculate the magnitude of a vector. So, for a vector A equals xi plus yj, or as a vector written as xy, we can illustrate this as shown. So here's the x part of A, and here's the y part of A, and this becomes a right-angled triangle as shown. The magnitude of a vector is mod A equals the square root of x squared plus y squared. A unit vector in the direction of A is A hat equals A over mod A. Let's now take a look at some notation. Use straight lines on either side of the vector. So mod A means the length of A, or mod xi plus yj, which equals mod of the vector A. Let's take a look at an example. If mod A equals 7, then A hat is equal to A over mod A, which equals A over 7. And it can be illustrated as shown. Now that we've reviewed the theory, we can take a look at the next exercise. Let's take a look at part A first. We have that mod A equals the square root of 3 squared plus 2 squared, which equals the square root of 13. And of course here we've used Pythagoras' theorem. And now for part B. Find A hat. So let's solve this. From part A we have that mod A equals root 13. And therefore A hat from the definition of a unit vector is equal to A over mod A. And simply plugging in the values gives us A, which is 3i plus 2j, over root 13, which is mod A. And this is our unit vector. And now for part C, we are required to find mod 2a plus b. So let's solve this. 2a plus b is as shown. So here's 2a and here's b. Let's expand the 2a, which becomes 6i plus 4j as shown, and leave the b as it is. Then we collect together the I terms, so 6i minus 2i equals 4i, and we collect together the j terms, so 4j minus 7j equals minus 3j. Now 2a plus b therefore equals 4i minus 3j, and therefore mod 2a plus b equals the square root of 4 squared plus minus 3 squared, which equals 5. So here's a summary of our solutions. Suppose the point P divides the line segment AB in the ratio lambda to mu, as shown in the diagram. So AP to PB equals lambda to mu, as shown. Suppose this is the origin here, and it joins A, and it also joins B and P. Then OP equals OA plus a fraction of AB. This fraction is lambda over lambda plus mu. And then replacing AB with position vectors gives us the expression shown here. We are now ready to apply this theory to our next exercise. Points A and B have position vectors A and B respectively, referred to the origin. The point P divides AB in the ratio 1:3. Find the vector OP. So let's sketch this. Here's our origin and the line AB. We also have the point P in the ratio AP to PB as 1:3. Here's the vector A, here's the vector B, and here's the vector P. If we apply our formula to this example, we obtain OP is equal to OA plus 1, which has taken the place of lambda, over 1 plus 3, which has taken the place of mu, times AB. And if we tidy up, putting the OA's together, we obtain 3/4 OA and the OB, which is 1/4 OB. And this, of course, is 3/4 A plus 1/4 B, where little a and little b are the position vectors. Now let's take a look at some theory relating to non-parallel vectors. So if A and B are two non-parallel vectors and PA plus QB equals RA plus SB, then we have that P equals R and Q equals S. So let's apply this to our exercise. The parallelogram OABC has a point P where the diagonals OB and AC intersect. The vectors A and C are equal to OA and OC respectively. Prove that the diagonals bisect each other. So let's solve this. From the diagram, we have that OB equals OC plus CB. This equals C plus A. And CB is equal to A, because CB is parallel and equal to OA. We also have that AC equals AO plus OC. And of course, AO is equal to minus OA. And OC remains the same. So we have that AC is equal to minus A plus C. And so we have AC equals minus A plus C. Now P lies on OB, as you can see from the diagram. And since OB equals C plus A, OP must be a scalar multiple of C plus A. Also, we have that P lies on AC. So therefore, OP, which equals OA plus AP, is equal to A plus a scalar multiple of minus A plus C. Since we have that AP is a fraction of the line AC. In particular, P lies on the line AC. And of course, this implies that lambda times c plus a is equal to a plus mu times minus a plus c, because both of these expressions are equal to OP. And so rearranging gives lambda a plus lambda c equals 1 minus mu times a plus mu times c. And since a and c are not parallel, we can conclude that lambda equals 1 minus mu and lambda equals mu. And so we have from both these equations that lambda equals 1 minus lambda. Rearranging this gives us that lambda equals a half. And since lambda equals mu, we have that mu equals a half also. And therefore, P is the midpoint of both diagonals. Since P lies on OB and AC, and OP equals a half times C plus A. And therefore the diagonals bisect each other. And so we've completed our exercise. This brings us to the end of this session. If you have understood its contents, you should be able to use column vectors and carry out arithmetic operations on vectors, calculate the magnitude and direction of a vector, use vectors to solve geometric problems, and find the position vector of a point dividing a line segment in a given ratio. Thank you very much for listening.